In today's video, let us discuss how real analysis falls to tools of stochastic calculus. The world of classical calculus, perfected over centuries, is a world of smoothness and predictability. It operates on the fundamental assumption that functions, when examined closely enough, behave like straight lines. This principle of local linearity, embodied in the concept of derivative, allows us to model the deterministic evolution of systems, from planetary orbits to fluid dynamics. However, when we turn our mathematical lens to phenomena governed by inherent randomness, this elegant framework begins to fracture. The mathematical idealization of random motion, known as the Brownian motion, exhibits properties so profoundly different from those of classical functions that it renders the tools of standard calculus inapplicable. The journey into stochastic calculus begins not with abstract equations but with a physical observation, the ceaseless erratic jiggling of microscopic particles. This phenomena, first systematically documented by Robert Brown in 1827, became the archetype for processes derived by a multitude of small random shocks. Albert Einstein in 1905 provided the theoretical explanation, arguing that this Brownian motion was the result of a particle being constantly bombarded by the molecules of the surrounding fluid. Each collision is a tiny independent event, and their cumulative effect produces the seemingly chaotic trajectory observed under a microscope. This physical model provides the crucial intuition for mathematical abstraction. The mathematical formalization of this process, known as the Wiener process, is convinced as the continuous time limit of a simple random walk. Imagine a particle on a line taking a small step left or right at discrete time intervals. As the size of the steps and the duration of the time interval shrink to zero, the path of the particles converges to a continuous random trajectory. This limiting procedure directly invokes the central limit theory, which dictates that the sum of a large number of independent random variables will be approximately normally distributed. Consequently, the changes in the position of an idealized particle over any time are governed by a normal distribution. Formally, a standard one-dimensional Wiener process denoted as Wt or Bt is a stochastic process categorized by four fundamental properties. The first one is that it starts at the origin, which means that W naught is equals to 0. The second property is that it follows continuous paths. The function is always continuous for almost every outcome. This means that the particle does not make instantaneous jumps or teleport. Its motion is connected through time. The next property is the property of independent increments. For any sequence of time 0 less than or equal to s less than t less than or equal to u less than v, the random variables representing the change in positions over disjoint time intervals wt minus ws and wv minus wu are independent. The past moments of the particles have no bearing on its future moments. The fourth property is that it has normally distributed increments. For any 0 less than or equal to s less than t, the increment wt minus ws is a normally distributed random variable with a mean 0 and a variance equal to the length of the time interval, t minus s. It is the interplay of these properties, particularly continuity and the nature of the increments, that leads to the process's most startling consequential feature, the paradox of its path. In elementary calculus, continuity is often a precursor to differentiability. While functions with corners or kinks are continuous but not differentiable at specific points, our intuition suggests that a continuous function should be differential almost everywhere. Brownian motion shatters this intuition in the most dramatic way possible. Its path is continuous everywhere but differentiable nowhere. The continuity of the path is an essential feature reflecting the physical reality that a particle must traverse a continuous trajectory through the space. One can metaphorically trace the path of a Brownian motion for Brownian particle without lifting the pen from the paper. However, the concept of a derivative lies on the existence of a unique tangent like a point. For a function to be differentiable, it must become increasingly linear as one zooms in on any given point. A Brownian path fundamentally defies this property of local linearity. A Brownian path fundamentally defies this property of local linearity. No matter the level of magnification, the path does not smooth out into a straight line. Instead, it reveals the same degree of erratic, violent oscillation. This property is known as self-similarity. The mathematical reason for this non-differentiability lies in the scaling of its increments. The derivative of the function ft at time t given by f dash of t is equal to as the limit h tends to 0, f of t plus h minus f of t by h. For a Wiener process, the increment wt minus wh is the random variable with a variance h. Therefore, the variance of the difference quotient is var of wt plus h minus wt by h is equals to 1 by h square into var of wt plus h minus wt. Now we know that the variance of wt plus h minus wt is equal to h. Therefore, the variance of the quotient is equal to 1 by h square into h, which will be equal to 1 by h. As the time interval h shrinks to zero, the variance of this ratio explodes to infinity. This means the difference quotient does not converge to a finite value. Instead, it oscillates with every increasing violence, preventing the existence of a limit. Thus, with probability 1, a derivative does not exist at any point. This single property, being continuous yet no way differentiable, is a most profound indication that the tools of classical calculus are insufficient for analyzing such processes. Failure of differentiation is only half the story. The other pillar of classical calculus, integration, also breaks down when confronted with the erratic nature of Brownian motion. Specifically, the standard framework for integration, the Riemann integral, relies on a property that Brownian paths conspicuously lack, which is bounded variation. For a well-behaved function f on a closed interval ab, one can measure the total distance it travels. This is formalized by the concept of total variation. We considered partition of the integral, pi, which is a sequence similar to this, where a is equal to t naught and b is equal to tn. And the sum of the absolute values of the functions changes over each subinterval. b pi of f is equal to sigma of modulus function of fti minus fti minus 1 from I is equals to 1 to n. The total variation of f is the supremum of these sums over all possible partitions. If this value is finite, the function is said to be a bounded variation. Intuitively, this means that the function does not oscillate infinitely or infinitely widely. Its total up and down moment is finite. All continuously differentiable functions, and more generally, all monotone functions, are of bounded variation. This property is a prerequisite for the existence of Riemann integral. A typical sample part of a Wiener process, Wt, is of unbounded variation on any time interval, no matter how small. The same scaling that causes non-differentiability is responsible for this property. The typical size of an increment, Wti minus 1, is on the order of its standard deviation, root over Ti minus Ti minus 1. For a finite partition of 0 to t into n subintervals of size delta t is equals to t by n. The sum of these increments behave like sigma of mod of Wti minus 1 from I is equals to 1 to n is approximately equal to, which can be also written as n into root over of t by n, because delta t is equals to t by n. Therefore, this will become square root of n into square root of t. So as the partition becomes finer, that is, as n tends to infinity, and this sum diverges to infinity. So as the partition becomes finer, that is, as n tends to infinity, this sum diverges to infinity. This confirms the intuition from the fractal coastline analogy. The path is so jagged that the total distance it travels is infinite. Because Brownian motion is not of a bounded variation, the Riemann integral is not well defined in the classical sense. This is a catastrophic failure. We cannot use the standard machinery of calculus to integrate with respect to a random process. Just when it seems that no sense can be made of the infinitesimal changes of a Brownian path, a remarkable and counterintuitive property emerges. Instead of assuming the absolute increments, let us consider the sum of squared increments over a partition pi. This is known as a quadratic variation. So, the formula for quadratic variation can be written as q pi of w is equal to sigma of wti minus 1 square from I is equals to 1 to n. For any ordinary differentiable function f, this sum converges to 0 as the partition becomes finer. The increments fti minus 1 are approximately the derivative of the function fti into delta t. So the squared increments are of the order delta t squared. Summing these up leads to a quantity that vanishes in the limit. For a Wiener process, something entirely different happens. The expected value of each squared increment is exactly the length of the time interval. Therefore, E of var, which can be shown as expected value, is equals to var of wti minus 1, which is equal to ti minus ti minus 1. Summing these expectations gives E is equals to sigma of E from I is equals to 1 to n, which will be equal to sigma of ti minus 1 from I is equals to 1 to n, which will be equal to t. Now, this shows that as the mesh of the partition goes to 0, the sum of the squared increments converges not to 0, but to the deterministic value t. This convergence is not for every single path. This non-zero finite quadratic variation is mathematical signature of Brownian motion's randomness. It tells us that the infinitesimal changes of the process, while too large to be of order dt, are precisely of order root dt. Squaring them gives something of the order dt, which accumulates to a finite non-zero value. This peculiar property is the key that will unlock the door to a new form of calculus. The failure of classical calculus is not a collection of unrelated oddities, but a deeply interconnected chain of consequences stemming from the fundamental nature of the Wiener process as the limit of a random walk. This casual progression reveals that the properties of Brownian motion are not arbitrary. They are the logical and unavoidable mathematical consequence of modeling a process driven by the accumulation of countless independent random shocks. The failure of classical calculus is therefore is not a superficial issue but a deep structural one. The non-zero quadratic variation is not a bug but a feature. It is the precise mathematical quantity that captures the underlying randomness and will serve as the cornerstone of building a new stochastic calculus. The breakdown of classical calculus in the face of randomness forces a retreat to the first principles. Before we can define a new type of integral, we must first consider the very notion of size itself. How do we rigorously define the length of a set, the area of a region, or more importantly, for our purposes, the probability of an event? This fundamental question is the domain of measure theory, a cornerstone of modern real analysis. It provides the abstract and powerful language needed to build a new system of integration that is robust enough to handle the pathological functions that arise in the study of stochastic processes. The intuitive concept of length seems simple enough. The length of an interval, the length of a the length of the union of two disjoint intervals is the sum of their length. However, this in, however this intuition becomes surprisingly fragile. This intuition becomes surprisingly fragile when extended to more complicated sets. In 20th century, in the early 20th century, the mathematicians discovered that it is possible to define a length function that applies to every possible subset of the real line while simultaneously satisfying a few desirable properties such as countable additivity and translation invariance. This existence of the so-called non-measurable sets demonstrated that a more careful and restrictive approach was necessary. We cannot measure everything, so we must first define precisely which sets are measurable. This leads to the central concepts of sigma algebra, typically denoted by F or sigma. The sigma algebra on a sample space is a specific condition of subsets of sample space that we deem to be measurable. It is not necessarily the set of all subsets, but rather a well-behaved family of them. For a collection of subsets F to be a sigma algebra, it must satisfy three axioms that capture our intuition about how measurable each should combine. The first axiom is that the whole space is measurable. If we are measuring parts of a space, we must be able to measure the entire space itself. This means that the sample space should belong to F. This means the sample space should belong to F. In probability, this corresponds to the fact that event some outcome occurs must have a well-defined probability, which will be 1. The next axiom is that it should be closed under complementation. If a set A is in F, then its complement must also be in F. The next property is that it should be closed under countable unions. If A1, A2, A3, and so on is a countable sequence of sets in F, then their union must also be in F. This property is what makes sigma algebra powerful enough for analysis. It ensures that we can handle limiting processes, which are ubiquitous in calculus and probability theory. A pair denoting the sample space and the sigma algebra is called a measurable space. Once we established which sets are measurable, we can define a function to measure them. A measure denoted by mu or p is a function that assigns a non-negative extended real number to each measurable set in the sigma algebra. It must satisfy two key properties. The measure of empty set is always 0. The next property is that for any countable sequence of disjoint measurable sets A1, A2, and so on in F, the measure of the union is the sum of their individual measures. This property is a rigorous generalization of an intuition that the whole is the sum of its parts. A triple containing the sample space, the sigma algebra, and the measure function is called the measure space. The canonical example of a measure is the Lebesgue measure, denoted by lambda on the real line. It is a unique measure on the Borel sigma algebra. With the foundational machinery of measure theory in place, we can now construct a new theory of integration that is more far powerful and general than the one developed by Riemann. The Lebesgue integral is built directly upon the concepts of sigma algebras and measures, and its novel approach resolves the limitations of Riemann integral. The fundamental difference between Riemann and Lebesgue integrals lies in how they approach the task of calculating the area under a curve. The Riemann integral partitions the domain of the function, whereas the Lebesgue integral partitions the range of the function. Instead of vertical rectangles like the Riemann integral, the area is approximated by wide, short, horizontal slabs. The process is as follows. First, partition the y-axis into small intervals. For each small interval strip, say yi to yi plus 1, we look back to the domain and ask for which x values does the function f of x fall within these strips. This set of x values, ai belongs to x such that yi is less than or equal to f of x is less than yi plus 1 may be a complicated, disconnected set. Here, the power of measure theory becomes essential. If this set ai is measurable, we can find its size or total width using the measure u of ai. The contribution to the integral from this slab is then approximately its height by I multiplied by its total width, mu of ai. The Lebesgue integral is the limit of these sums as the height of the horizontal slabs goes to zero. As the height of the horizontal slabs goes to zero. In Lebesgue's analogy, this is the shopkeeper. This is this is like the shopkeeper first emptying the register, sorting all the coins and bills by denomination, and then counting each by. This is the mathematical formulation of the Lebesgue integral. The abstract and powerful framework of measure theory developed to solve problems in real analysis turned out to be a perfect tool to place probability theory on firm axiomatic foundations. Prior to the 20th century, probability was often a collection of methods and intuitions, lacking a unified mathematical structure, especially when dealing with infinite or continuous outcomes. By recasting probability in the language of measure, the Russian mathematician Andrei Kolmogorov provided a rigorous system that could handle the complexities of modern probabilities, including the study of continuous time stochastic processes. The modern foundation of probability theory is the probability space, which is simply a measure space where the total measure of the space is equal to 1. This elegant construction, defined by Kolmogorov's axioms, consists three components. 1. The sample space. 2. The sigma algebra of the events. And 3. The probability measure P. This measure theoretic formulation provides a single unifying framework for all of probability, from a discrete conflict to the infinite dimensional spaces required for stochastic processes. It gives us a rigorous way. It gives us a rigorous way to handle the concept of randomness in continuous time space. With the probability space defined, we can now give a rigorous definition of one of the most fundamental concepts in probability, the random variable. Informally, we think of a random variable as a number whose value is subject to chance. Formally, a random variable is not a variable at all. It is a function that maps outcomes from the sample space to a set of values, typically the real numbers. Crucially, it's not just any function, it must be a measurable function. A function x is defined as a random variable if it is a measurable function from the probability space omega fp to the measurable space of the real numbers R, BR, where BR is the Borel sigma algebra on R. The condition of measurability is the linchpin that connects the abstract probability space to practical calculations. It requires that for any well-behaved set of real numbers, B belonging to Borel algebra BR, on an interval like A, B, its pre-image under the function x must be the event in our sigma algebra. That is, probability of x belonging to B should be equal to probability of W belonging to omega such that x of W also belongs to B. This condition might seem technical, but its importance is profound. It acts as the essential bridge that allows us to assign probabilities to the values taken by the random variable. Finally, a stochastic process can be formally defined as a time-indexed collection of random variables, all defined on the same underlying probability space. This provides the complete rigorous foundation needed to begin building a new calculus. Armed with the robust machinery of measure theory and a rigorous axiomatic formulation of probability, we are now equipped to tackle the central problem, defining an integral with respect to a process like Brownian motion, whose parts are of unbounded variation. This new integral, the Itos integral, lies at the heart of stochastic calculus. Its construction is a masterful application of analytical tools we have developed, relying on approximation by simpler processes and a specific type of convergence that is particularly suited to the statistical nature of the problem. First, let's look into the construction of the Itos integral. The objective is to give mathematical meaning to this expression, integral of hs dws from 0 to t, where ws is a Wiener process and hs is another stochastic process called the integral. Since the bounded variation of ws precludes the use of Riemann integral, a new approach is required. The construction pioneered by Kiyoshi Ito proceeds in stages, building from simple cases to the general one through a limiting procedure. The construction begins with the simplest possible class of integrands, simple process. A simple process, Hs, is one that is piecewise over a partition of the time interval from 0 to t. So, in this step, we partition the time interval, making n intervals, where t of 0 equal to 0 and t of n is equals to t. So we can write HSDWS from 0 to t as sigma of HTI minus 1, WTI minus 1 from I is equals to 1 to n. Here, HS is equal to HTI minus 1. A critical and non-negotiable feature of this definition is the choice of evaluation of the integrand h at the left endpoint, t minus 1 of each integral. This is not an arbitrary choice, as it would be in a Riemann integration. It is a mathematical enforcement of causality and is tied up to the concept of adaptedness. A stochastic process, HT, is said to be adapted to a filtration FT if, for every time t, the random variable HT is measurable with respect to the sigma algebra FT. The filtration FT represents the accumulation of all information available up to time t. The adaptedness condition means that the value of HT cannot depend on the future events. By choosing the left endpoint t minus 1 to determine the value of the integrand, we ensure that a decision is made only on the information available before the subsequent random increment of the Wiener process. This choice ensures that the resulting integral process is a martingale, a process whose expected future value given the present is simply its present value. In the next step, we will look into the Ito isometry. This is a crucial step which is necessary to establish a property for the integral of simple process that will allow us to extend definition to a much wider class of integrals. This property, called the Ito isometry, relates the second moment of the stochastic integral to a standard Lebesgue integral. For a simple process H's, the isometry states that the expected value of the square of integral of H's dws from 0 to t is equal to the expected value of the integral of hs square ds from 0 to t. The left-hand side is a variance of the Ito integral, which is a random variable. The right-hand side is the expectation of the standard Lebesgue integral of the squared process hs square. This remarkable formula connects the geometry of a random space with that of a deterministic one. It is proven by expanding the square of the sum using the independence of non-overlapping increments Ws and the fact that E is equals to Ti minus 1. The Ito isometry is the engine that derives the entire construction as it provides a way to measure the size or norm of the integral. The final step is to extend the integral from simple process to a much larger class of adopted processes. This is run via an approximation argument that is standard in real analysis. The target class of integrants is a space of adapted hitches that are square integrable in a specific sense, namely that expectation of integral of h square ds from 0 to t is less than infinity. This space is often denoted by L square b or a similar notation. So the argument proceeds as follows. It can be shown that any process Hs in this larger class can be approximated by a sequence of simple processes Hsn such that the approximation error goes to zero in a mean square sense. Therefore, on limit of n tends to infinity, the expected value of integral of Hs minus Hsn whole square ds from 0 to t should be equal to 0. We then consider the sequence of Ito integrals of these simple processes. In is equal to integral of Hs and Ws from 0 to t. Using the linearity of the integral and the Ito isometry, we can show that this sequence is a Cauchy sequence. Therefore, we can write this as integral of Hs Ws from 0 to t is equal to limit of n tends to infinity on the integral of Hs n dws from 0 to t. This three-step process, defined for simpler functions, establish an isometry, and extend by completeness, is a classical technique in functional analysis. Here, it allows us to give a rigorous meaning to an integral that was previously undefined, built entirely upon the foundations of measure theory and Lebesgue integration. The construction of the Ito integral relies on the concept of limit. However, when dealing with the consequence of random variables, the notation of the convergence is more suitable than for deterministic sequences of numbers. There are several different ways a sequence of a random variable can converge, each capturing a different aspect of getting close to a limit. The Ito integral is defined using a specific mode of convergence, convergence in mean square. Understanding why this mode is used and not others is key to grasping the nature of stochastic calculus. To understand convergence in mean square, it is helpful to adopt a geometric perspective from a functional analysis and think of random variables as vectors in an infinite dimensional space. The space of all random variables x defined on probability space omega fp that has a finite second moment, which means that expectation of x square is less than infinity, forms a vector space known as L square on omega fp or simply L square. In this space, an inner product between two random variables x and y can be given as E of xy. The inner product induces a norm or notation of length for each vector given by length of x on L square is equal to root of expected value of x square. The distance between two random variables x and y is the naturally defined as the norm of the difference, which is equal to x minus y. The distance which is equal to root over of expectation of x minus y square. An L square space equipped with the structure is an Hilbert space, a complete inner product space. A sequence of random variables xn is said to converge in mean square to a random variable x if the distance between them in this space goes to 0. That is, limit n tends to infinity, xn minus x on L square is equals to 0, or limit n tends to infinity, expected value of xn minus x whole square is equals to 0. This does not mean that for a specific outcome w, the number xn of w necessarily gets closer to xw. Instead, it is a statement about the average squared error over the entire sample space omega. The probability of large deviations becomes small, and the magnitude of those deviations is also controlled. A stronger and perhaps more intuitive form of convergence is almost sure convergence. This would mean that for almost every outcome, W belongs to omega, the sequence of real numbers xn of W converges to the real number xw. This corresponds to our idea of path-by-path convergence. This can be mathematically written as this: probability of xn is equals to x, where n tends to infinity, is always equal to 1. With a well-defined theory of stochastic integration, the final piece of the puzzle is to develop a corresponding theory of differentiation. Specifically, if we have a stochastic process xt and a smooth function f of t comma x, what is the differential of the new process yt, which is a function on t and xt? A naive application of the multivariable chain rule from the ordinary calculus would be incorrect and would lead to significant errors. The correct chain rule for stochastic calculus is Ito's lemma, a formula that stands as one of the most important and widely used results in the field. So, to understand Ito's lemma, let us consider this process. D of xt is equal to mu t dt plus sigma t dwt, where mu t is a drift term and sigma t is a diffusion term. Now, we have to find a small change of a function yt, which is a function on t comma xt. So, using Taylor's expansion, this can be written as delta y is approximately equal to partial derivative of f with respect to t into delta t plus partial derivative of f with respect to x into delta x plus half into second order partial derivative of f with respect to x into delta x square plus smaller terms. Now we establish a set of rules of thumb for the products of these infinitesimal quantities based on their order of magnitude. According to these rules of thumb, dt squared tends to 0, dt into dwt also tends to 0, and dwt squared tends to dt. Now, substituting delta x, which is equal to mu into delta t plus sigma t into delta wt into the Taylor expansion of delta y, we get dyt is equals to partial derivative of f with partial derivative of f with respect to t into dt plus partial derivative of f with respect to x into dxt plus half into second order partial derivative of f with respect to x into sigma square into dt, which expands to dyt is equals to partial derivative of f with respect to t plus mu into partial derivative of f with respect to x plus half into sigma t square into second order partial derivative of f with respect to x whole into dt plus sigma t into partial derivative of f with respect to x into dwt. This is the Ito's lemma for calculating a small change of a function on t, xt. Ito's lemma is a fundamental theorem of stochastic calculus. It is the engine that allows us to manipulate and solve stochastic differential equations. Its application in quantitative finance are vast. For example, it is the control tool used to derive the famous Black-Scholes partial differential equation for options pricing by constructing a risk-free portfolio whose value dynamics are determined using Ito's lemma. It provides the essential bridge between the dynamics of an underlying random asset and the dynamics of any derivative security written upon it. The journey from the erratic dance of a pollen grain to the sophisticated machinery of a stochastic calculus is a testament to the power of mathematical abstraction and rigor. It is a story of how the limitations of one mathematical framework motivate the construction of a new, more powerful one. This video has traced the logical arc of this development, demonstrating that stochastic calculus is not merely an extension of classical calculus, but a fundamentally different paradigm built upon a new foundation. Faced with this breakdown, real analysis provided the language and tools for complete reconstruction. The narrative began with the central problem, the mathematical model for pure randomness. The Wiener process possesses a set of properties that are fundamentally incompatible with the tools of deterministic calculus. Its sample paths, while continuous, are so violently erratic that they are no way differentiable and possesses infinite total variation on any interval. These are not mere curiosities. They are direct mathematical consequences of modeling a process driven by the accumulation of countless independent shocks, a model whose scaling behavior is governed by the square root of time. This pathological nature rendered both the classical derivative and the standard Riemann integral useless for describing the dynamics of random systems. Faced with this breakdown, a retreat to the first principles was necessary. Real analysis provided the language and the tools for a complete reconstruction. Measure theory provided a rigorous way to define the size of sets, moving beyond the intuitive but limited notion of length. The concept of sigma algebra allowed for a precise definition of which collections of outcomes or events could be measured, while the measure itself provided the function of quantifying them. Upon this foundation, the Lebesgue integral was constructed. By partitioning the range of a function rather than its domain, it offered a more general and powerful method of integration, capable of handling highly discontinuous functions, and most critically, possessing superior convergence theorems that allow for the robust interchange of limits and integrals. The measure theoretic framework was then used to place probability theory on a firm axiomatic footing. The probability space omega fp became a measure space of a total measure 1, and a random variable was rigorously defined as as a measurable function mapping the outcomes to the real values. This framework was capable of handling the uncountable infinite dimensional sample spaces required to model the continuous time process. With this new solid foundation in place, the edifice of stochastic calculus could be erected. The Itos integral was constructed as a limit of subs, but this limit was not the pointwise limit of a classical calculus. Instead, it was a limit in the L square or mean square sense. This choice was not a compromise, but a natural adaptation to the statistical nature of the problem, focusing on the convergence of moments like mean and variance rather than the convergence of every individual and erratic path. The Ito isometry provided the key analytical tool to prove the existence of this limit. Finally, the Ito's lemma emerged as a correct chain rule for this new calculus. It explicitly incorporates the unique non-zero quadratic variation of the stochastic process through an additional second derivative term, providing the foundational tool for analyzing and solving stochastic differential equations. In conclusion, real analysis is not merely a technical prerequisite for the study of stochastic processes. It provides the very grammar and syntax in which the theory is expressed. It supplies the rigorous definitions of size, integrability, and probability that are necessary to make sense of randomness in a continuous world. It forges the analytical tools of convergence and completeness that allow for the construction of the new mathematical objects, like the Ito integral. It provides the indispensable mathematical backbone that transforms the intuitive idea of a random walk into the powerful and predictive framework of stochastic calculus, a framework that has become essential in the fields ranging from financial engineering and physics to biology and control theory.